In the past I have published quite a few videos about square wave oscillators on my YouTube channel, and you can find them. Go to my channel trailer Radio Fun 232, go there to the looking glass and type there the keywords, say square wave oscillator, sawtooth wave oscillator, radio, VLF, etc, etc. Say all the keywords via which you can find my videos. There are approximately 1700 videos on my YouTube channel, and there are also 2 books on the Lulu website via which you can say directly click through to all these videos, but not all of them. I have to say that because it's these 2 books go say to approximately 1200 videos, and now I am on 1700 videos anyway. I did not want to elaborate so much on that, but anyway, here is the circuit that I want to talk about. It is that square wave oscillator. It was here, and the principles are very simple. You find this circuit on many in many old school radio magazines, and it is say a multivibrator, but I have connected here a second stage via which you can take out that frequency low impedant, and you can also connect here a potentiometer to say make the output variable in terms of voltages. The circuit is very simple. Here is a voltage regulator via which we send in to that multivibrator different voltages, and these voltages are responsible for the frequency band, and the capacitor here Cx is responsible also for the frequency band, but more say the central frequency where it works. I have to say there is here also a bias potentiometer. You can turn it, and via that way you can set the pureness of the waveform, and here you set the frequency. So let's see what this can bring. Voltage supply is 24 volts, and I needed that 24 volts to get a voltage span, and that voltage span is responsible for the frequency. Well, Cx is more or less the key here. It sets the frequency, test it, different frequencies and different capacitors, of course. NP means non-polar. 1500 picofarad, we are on 452 kilocycles. 10 nanofarad, we are on 10 kilocycles. 470 nanofarad, that is 0.47 microfarad, we are on 2.6 kilocycles. And with 100 microfarad, we are on say 12 hertz. But the waveform is very bad. Well, let me show it. This is that 1 nanofarad capacitor, that is 1000 picofarad. This is the waveform. And we are on 700 kilohertz, kilocycles. That is quite high, and I think that this is a quite good waveform given that high frequency and a very simple setup of this schematic. Well, let me show what it means when you change the bias here via this potentiometer, that is 250 kilo ohms, that is here, this one. I turn it now and let's see what happens. So here you see that, well, the amplitude drops very substantially. I think it's not a problem, but anyway. And also you can see that is in a certain way a little bit strange, but anyway the frequency changes somewhat. 651 kilohertz has, in my opinion, to do with the damping of the oscillator. So 685, so biasing and damping come together. And of course there is the frequency potmeter that is here, this one, and that is this potentiometer, 47 kilo ohms, sets the output voltage between, say, I think 2 volts and 20 volts or so. Let's see what happens when we turn the voltage to this generator. Also in that case the frequency changes and the waveform changes. So 514 kilohertz, 586, and I've tested it yesterday and I found that the frequency stability is, in my opinion at least, good enough for hobby purposes. Now we are on 587 kilohertz. So go to the somewhat bigger capacitor, that is 1500 picofarad. That's here now, that yellow one. We are on, we have this waveform, and that depends again on the bias setting, and we have this frequency 380 kilohertz. Change the bias first. Let's see what happens. Of course the waveform will substantially change. Here. Here it stops. The bias is not okay. It is not able to, the final transistor is not able to amplify it. So here the waveform turns back. And we are on 385 kilohertz. Turn the frequency potmeter again. Here. So this one with a screwdriver. Let's see what happens. And yes, we see a substantial change in the frequency. 455, say 455 kilohertz. 3 to 4 kilohertz. Well, I think I touched the circuit. Of course, it is say experimental. 245, 242 kilohertz waveform, etc., etc. So let's go to 10 nanofarad. That is 0.01 microfarad. Here we have the waveform. Quite good in my opinion. We are on 106 kilohertz. By changing the bias we can perhaps get a more sharp, yes, that is successful, changing the bias, get a more sharp square wave, 106 kilohertz. Again, let's look to the frequency perhaps it is too lengthy, but anyway, I hope not too lengthy. And here we see the amplitude change, but also the frequency. Now we are on 68 or so, 67 kilohertz with this waveform. I think it's useful for certain purposes, for a fixed frequency or a test oscillator of whatever kind. Now I'm connecting the 100 microfarad cap, that's here, the blue one, and here we see the waveform. And it's a kind of needle wave. We are on 11 Hertz, so no, say, proper square wave. But anyway, let's try the bias, perhaps that will help a little bit. Yes, it helps a little bit. And when you are doing all these experiments, I've done them through many years, you will always see these kinds of, say, waveforms in the lower frequency band. And then I mean between, say, 5 Hertz and 30 Hertz. Perhaps with a 555 that will work better, but anyway, we are on 12 Hertz, 13 Hertz. Anyway, turn the frequency potmeter again here. Let's see what happens. Well, the frequency changes somewhat. Anyway, that's all that I wanted to tell. Thanks for watching. Very simple circuit, by the way. Could be useful for all kinds of purposes. You can use it and develop it further for a fixed frequency or as a test oscillator. In that case, well, you have to do perhaps somewhat more research, but anyway, I think it is a useful circuit. Thanks for watching again.